Next question is asking about the splitting of water into hydrogen and oxygen, so putting that into kind of an equation, be H2O going into H2 plus half O2. So that's the direction it's describing. We're given entropy values for all the things in that equation, so the entropy value for water, well basically steam, and then into hydrogen and oxygen. First part defines an entropy, just a straight one out of the notes. It's the measure of disorder in a system. Remember, in a system just means kind of like in an enclosed space or in like a reaction you're studying yourself. 7b, suggest and explain the effect on the entropy change of liquid water is used instead of gaseous water. Now this is a hard question, involves using a wee bit of logical thinking here. If we imagine like a little entropy scale, kind of like a graph, where entropy is going up and the higher you get in the scale. If I describe the change kind of visually, if this is the entropy of steam, and then I'm going to look at the entropy of the two gases it splits up into, so hydrogen and oxygen. I could actually work at the numbers here, it'd be fine, but I can't even just kind of inspect the equation. I've got 1 mole of gas on the left hand side, I've got 1.5 moles of gas on the right hand side. That's always going to cause the entropy to increase. So no, you could use the numbers here to check that, but it's going to be like that. So entropy is going to be higher in the products here when I get it to H2 plus a half O2. So we've got an increase in entropy. The question says, if I, instead of using steam, gaseous water for this change, and use liquid water instead, what effect would that have on the actual entropy change value without having to use any numbers? If you think about it from what we had in the notes, the entropy of a liquid is always going to be lower than the entropy of a gas, because the liquid, or particles closer together, can't move as much less disorder than there is in the gas. So if I was put on the scale, I would put H2O liquid a little bit lower. But if I'm doing the same change, if I'm splitting it up into gaseous hydrogen, gaseous oxygen, it's still going to end up at the same finishing point. So I'm starting from a lower starting point, but ending at the same finishing point. Therefore, the overall change, the overall increase in entropy will be much, much bigger. So that's kind of what the question was about. It's worth 2 marks. First part was just getting it the correct increase or decrease. So it's going to increase the entropy change. And you don't need like a really big, long explanation, but basically you're talking about the entropy of liquid water is lower than the entropy of gaseous water. And that more or less answers the question. Then we get on to question 8, which is a bit of a tricky one, and probably a little bit too tricky, probably a bit too hard for this test. It's from another exam board, and does require a wee bit of information, which is probably a wee bit too far beyond what we've covered so far. So I'm going to explain how, the proper justification for it. Again, as I said, we're not really expecting you to have got this perfectly, and we did decide to take it down just being out of 1 mark for this one, be a bit more generous to you. So the question describes a reaction between carbon monoxide and hydrogen. It tells you about all the conditions, but basically the question says, if you do it at 100 degrees C, you get a better yield than you get at 250 degrees C. It asks you to explain in terms of entropy change of the surroundings and total entropy change of the reaction why this is so. You could have tackled this question using Le Chatelier's principle in terms of temperature in the reaction. Probably why a lot of you didn't do that is because the question quite explicitly says, talk about entropy, which made it trickier. If you did go down the Le Chatelier's route, it's actually not that hard a question because it's an exothermic process, tells you to start. So therefore, if you increase the temperature, you're going to favour the reverse endothermic process, going to push the equilibrium back to the left, reduce the yield. But I can see why a lot of you didn't do that because the question didn't really say you could. In terms of entropy change of surroundings, that's actually the bit we haven't really covered in our spec, which made this question a bit hard. But I'm going to go through it just in case you're interested and just maybe to alleviate any concerns if you think you should have got this question. What we've done in this topic and what CA do in their spec is just give you this equation, delta G equals delta H minus T delta S. I mean, just kind of take it from nowhere and just say this is the equation. In other exam boards, you kind of look a little bit about where that comes from. Where this actually comes from is the second law of thermodynamics, which is that entropy of the universe always increases. You might have heard that before. So entropy always increases. That might kind of seem a wee bit contradictory because we have looked at some chemical reactions where entropy tend to decrease. That doesn't actually break that law. Basically what happens in any kind of reaction is you're talking about the entropy of the universe, so delta S universe, is the sum of two parts. delta S of the system, so remember we used that word system before, just means like your reaction you're looking at, but also the entropy of your surroundings. So in other words, your entropy of your system could decrease as long as the entropy of your surroundings does increase in respect to that. Entropy of surroundings is basically controlled by how much heat your reaction is producing. So that's where entropy comes into it. So delta S surroundings is the sum of minus delta H over T. That's just, I'm bringing that sort of out of nowhere. That's just like a mathematical relationship. If you've got a very exothermic reaction that produces a lot of heat, that causes the gas particles around your container, your beaker reactions taking place in, to heat up and move more quickly, to become more disordered. That increases entropy. So mathematically we put a minus sign because remember exothermic is negative because it's a positive entropy change, so you have to make it change the sign. And we divide by temperature because that effect becomes less the higher your temperature is. If the particles around your container are already very hot and moving very quickly, you having an exothermic reaction isn't going to make as big a change. So it's modulated by temperature. Subbing that back in, so we get delta S system, which is the change of entropy of a reaction, equals, plus minus delta T, delta H over T. What we do is a wee bit of manipulation. So we're going to multiply everything by T. So T delta S universe equals T delta S system plus minus delta H. I don't like that minus, going to turn anything else into minus. So minus T delta S universe equals minus T delta S system plus delta T. And if you actually rearrange this a wee bit, minus T delta S is actually what we call delta G. That's its actual derivation. Delta G equals delta H minus T delta S. It's T delta S system, our reaction, but we just dropped the system at this point. So that's where the actual free energy equation comes from, this derivation from the second law of thermodynamics. Why I've gone through all that is actually relates to the question. Explain in terms of entropy change of the surroundings, why it decreases to have the higher temperature. It's actually going back to this bit right up at the very top I mentioned about the entropy of your surroundings. The higher temperature is, the less an effect an exothermic reaction has on being favourable. So in other words, the higher temperature at 250, the delta H contribution to the increasing entropy of the surroundings is going to be less. That's what the question was about. I think it's very hard, but that's what is reaching towards. If it did come up in a CA exam, it would be along the lines of Le Chatelier, that question. You could answer it in terms of endothermic, exothermic as well. 9b you could do, and I'll love you to get this. So it's, even if you didn't get the first part about explaining why the yield decreases at a higher temperature, you could explain why you want to carry it at the high temperature anyway, because we talked about that law with equilibrium in AS. It's a kind of a compromise, yield versus rate. So therefore, at a higher temperature, you must have a much higher rate, which can be favourable even if your yield isn't perfect. So you carry it at 250 anyway, because the rate is higher at 250. Final question 10c, which reaction is the most positive entropy change for the system? S system, so just means entropy of the reaction. Just a standard multiple choice to kind of analyse it just without using numbers. So the first one, you got aqueous solution, going aqueous solution plus liquid. Those ones can be tricky. To be honest, you're never really going to get a massive change in entropy if everything's just in a beaker in like kind of liquid form or dissolved form. Aqueous solids, aqueous solutions, so particles dissolved in water, they can move by quite freely. There's quite a lot of disorder there. In the same way that liquids can move by quite freely. So going from two things moving as liquids to two things moving as liquids is going to be that big a change. This next one, we're going from an aqueous solution to a solid plus aqueous solution. That's still going to decrease entropy because you're going down to a solid, which is very ordered. Next one, you've got a gas and the gas going to liquid. Again, that's going to decrease entropy because liquids are have lower entropy than gases. Last one, 1 mole of gas going to 2 moles of gas. That's going to be one because you're always going to increase entropy if you're making more particles of gas in a reaction. So that's standing out as the correct answer there.